Okay, welcome to this uh, uh, class. We want to now provide the solution to the instrumentation tutorials problems. Now, we earlier posted 2 weeks ago. So to find the questions to this tutorial solution, you can check the channel. You will see the link to that video where we provided the questions to test yourself in the channel. So this is Electro Teach channel, the channel whereby we teach good knowledge in engineering, in electronics, instrumentation, computer, mathematics. So welcome once again. If you are a subscriber, thanks for coming back to see my video. If you haven't subscribed, please subscribe to the channel, click like and share the video as well. So don't skip any part of this video in order to get all the solution clearly, how we got or why we arrived at the solution provided to each problem. So now, without wasting much time, let's move on to the first question and its solution. The first question is to explain in details the resistance method of temperature measurements. The resistance method of temperature measurements. Now, you recall that materials, different materials exhibit different property when it comes to application of heat. The resistance method of temperature measurement works on the principle of resistivity. And for a metallic conductor, the resistance is proportional to its length and inversely proportional to its cross-sectional area. All right, so we can see on the screen here the formula R equals rho L divided by A, where R is the resistance of the material, not resistivity, resistance of the metallic conductor, and L is the length of the wire measured in meters. A is the cross-sectional area of the wire in meters squared, and rho is the Greek letter representing the resistivity of the material of the wire measured in ohm meter. Okay, so these are the property of a metallic conductor. Now, the resistivity of the material changes with a change in temperature, thus resulting in a change in resistance. So in other words, we can see that resistivity is a temperature-dependent property of a metal. It's temperature-dependent. And so this property is used for temperature measurements. So any method that we can use to vary any of the quantities above, whether the length of the material, the resistivity, or the area, the cross-sectional area, can form the basis of an electrical resistive transducer. So electrical resistive transducer can be made using any of the above variables. So, but mostly the resistivity changes due to change in temperature. So we can utilize that change in resistivity as a result of change in temperature to construct a resistive method of temperature measurements. So we have common devices that work on this principle, and these are potentiometers and strain gauges. They are based on resistance change brought about by change in temperature. So that is the explanation of that. That is the solution to question number 1. So if you can explain this way, you will get a full point for this question. Now let's look at question number 2. Question number 2 is a calculation based on the flow measurements in a channel. Flow measurements in a channel. So we can We can see the question on the screen. The question says, in a hydraulic system, water having specific weight of 9.81 kilonewton per meter cube flows in a channel from point A to point B at a rate of 0.37 meters cube per second. In the previous question given, there's a typographical error. This was written as meter square per second, but actually it should be meter cube per second. That's the right unit because it's a quantity, the volume of water that flows per second in the channel. Now, point A has a diameter of 300 millimeter and is 4.5 meter below point B, which has 600 millimeter diameter. So the question is, calculate the pressure at point B. The pressure at point A is 66.2 kilopascal. All right, so we want to determine the pressure at point B. If the pressure at point A is 66.2 kilopascal, and we are here we have the solution. Solution is here. We have the diameter of the pipe at point 1 is 300 millimeter. The volumetric flow Q1 at point 1 is 0.37 meter cube per second. Then we have Z2 minus Z1 is equal to 2 meter because point B is higher than point 1, than point A, and that means Z2 is above Z1. So Z2 minus Z1 is 2 meter. You can realize here that they didn't give us the specific heights for point 1 and point 2, or point A and point B. But you could see the difference between them by just writing it this way. Z2 minus Z1 is equal to 2 meter. The diameter of the pipe at point 2 is also 600 millimeter. And the pressure at point 1 is 66.2 kilopascal. That's gauge pressure. So we want to find out what is the pressure at point B, that is P2. So we will go and approach this problem by employing the Bernoulli's equation, as we have on the screen here. Bernoulli's equation. P1 over gamma plus Z1 plus V1 squared over 2G equals P2 over gamma plus Z2 plus V2 squared over 2G. All right. So now we are trying to find out P2. So we could make P2 subject of relation by following these two steps. So P2 over gamma is equal to P1 over gamma plus Z1 plus V1 squared over 2G minus Z2 minus V2 squared over 2G. So this implies that P2 equals gamma, open the brackets, P1 over gamma plus Z1 plus V1 squared over 2G minus Z2 minus V2 squared over 2G. So this is applicable formula that we want to employ to determine P2. But looking at this formula, we could realize that there are one or two unknown left. So we need to actually find that. And then we can rearrange this formula to get this. If we rearrange it, we can have P1 plus gamma, bracket open, Z1 minus Z2 plus V2, V1 squared minus V2 squared divided by 2G, as we have it here. So you can see as this one is a simpler form of the formula that we have above. So we are going to utilize this. Now, to look at the equation here, we see that we still don't have the value of V2. We are given V1. But we can employ continuity equation to determine V2 as follows. Continuity equation states that A1 V1 is equal to A2 V2. The cross-sectional area and the velocity of flow is used to obtain the continuity equation at any particular section of the channel. So we can make a V2 the subject of formula. V2 equals V1 multiplied by A1 over A2. And then we can determine A1 by using the diameter. We can use the diameter given, which is 300 for point 1 in the channel. As you can see on the screen here, pi d1 squared divided by 4. Pi multiplied by 300 squared divided by 4 gives us 70714.3 millimeters squared, or 70714 times 10 to the minus 6 meters squared. That is the area at point 1 Now, having got that, we can use the volumetric flow to determine the velocity when we have the area like this. So V1 is equal to Q. The formula is V equals Q over A. Thus, V1 equals 8.37 divided by 0.0707. And that is 5.23 meter per seconds, 5.23 meter per seconds. Okay, now we can now determine the value of V2 using the continuity equation from here. You can see the continuity equation here. So you can substitute the three parameters here into the equation. We have V2 equals 5.23 times 90,000 divided by 360,000. That is, if you use the diameter in place of the area. So since we have the area is pi d1 over 4 for A1 and pi d1 over 4 for A2. So pi over 4, we neutralize each other, the numerator and denominator. So we have d1 squared over d2 squared left. That is why we use only that here. So that is it, d1 squared here and then d2 squared here. And the answer here will be 1.3075 meter per second. So we can now, we thus determine the velocity at point 2 in that manner. Now we can now go back to the Bernoulli's equation and substitute the values. So therefore, P2 equals 66.2 plus 9.81, bracket open, and then Z1 minus Z2, as we have it on the screen here. We have Z1 minus Z2, but earlier we determined that Z2 minus Z1 is equal to 4.5. This is 4.5, not 2 meters, 4.5 meters, according to the question, according to what the question gave us here. We have 4.5 meter. So here is 4.5. Z2 minus Z1 is 4.5 because position B is higher than position 1. But in the equation, what we have is Z1 minus Z2. That means the value for this will be a negative value of what we have above. And that is why we have minus 4.5 in the equation. So that is why we have a minus 4.5 here, because channel at point B is higher than point 1, and Z1 minus Z2 from above is what we need. And so we can see that since Z2 minus Z1 is 4.5, Z1 minus Z2 will be minus 4.5. So if you substitute all the parameters into the formula, therefore we have P2 equals 66.2 plus 9.81 brackets minus 4.5 plus 5.23 squared minus 1.3075 squared. This divided by 2 times 9.81, you can get out of that 34.87 kilopascal, which is a gauge pressure. It is a gauge pressure. So we can see that. Okay. So that's a solution to question number 2. Straightforward solution. We can see that there are 2 pertinent formulas. That is the Bernoulli's equation and the continuity equation. Apart from the cross-sectional area that we have here, the Bernoulli equation and the continuity equation are the pertinent formulas that we employ in solving that problem. Now we want to move on to question number 3. It's also another calculation based on flow measurements. Another calculation based on flow measurements. A venturi tube of throw diameter of 62 mm is placed in a water pipe of diameter 110 mm to measure the volumetric flow. The volumetric flow rate through the tube is 0.08 meter cube per seconds, and the water has a density of 103 kilogram per meter cube and viscosity of 10 to the minus 3 Newton seconds per meter squared. So we can dive into the question now. Question 1, determine the Reynolds number for these conditions. And question 2, if the coefficient of discharge is 0.99, determine the upstream to throat differential pressure. And the solution, the area of throats can be calculated using our normal area formula. That is pi d squared over 4, as we can see here. So if you use that, we have pi over 4 times 62 times 10 raised to the power minus 3 squared. The answer is 3020.3 times 10 raised to the power minus 6 meters squared. So velocity of throat, V, equals the volumetric flow rate divided by the area. And that is what we have here. V is equal to Q over A. That's what we have here. That's what we use in the solution here. 0.08 divided by 3020.3 times 10 to the power minus 6. The answer is 26.49 meters per second, and that's velocity through the throat. Now, we can now calculate the Reynolds number. Reynolds number, represented as N subscript R here, equals V d rho over mu. As velocity, diameter, the rho and the mu. That is the formula for calculating the Reynolds number. So we have, if you substitute for everything in this equation, as we have gotten above, we have this 26.49 times 62 times 10 to the power minus 3 times 10 to the power 3 divided by 10 to the power minus 3. And we have 1.64 times 10 to the power 6. That's the Reynolds number. We could see that the Reynolds number is a little bit higher than 10 to the power 5. So we can assume that this is a turbulent flow. This turbulent flow is greater than 100,000. The Reynolds number is greater than 100,000, so we can assume that the flow is a turbulent flow. Now we move on to the part 2 of the question. We are told to determine, to calculate the upstream to throat differential pressure given the coefficient of discharge at 0.99. So we have to determine the upstream to throat differential pressure. And that's what we are going to solve now. So let's look at the solution to that one. So the solution is here. E equals root 1 minus A1 over A2 squared. So we can determine E from here. So if we substitute A1 and A2, we can use their diameter for this substitution since we have a ratio. So we have 1 minus 62 over 110 and bracket squared. Then we take the square root of that. With that, we can come out with 0.826 as the value of E using those formula. Okay, using these parameters. Now the Q, the flow rate, Q equals CEBA A sub Y, square root of 2 delta P over rho. So if you substitute that, we have Q equals 0.99 times 0.826 times 1 times pi over 4, 62 times 10 to the power minus 3 squared. That is the area at that point, A sub Y. We use sub Y to identify that point. Square root of 2 delta P divided by rho. And the rho is 1 times 10 to the power minus 3. So we make delta P the subject of the relation here, and then we equate it to 0.08. Then we are going to come out with delta P equals 525.02 kilonewton per meter squared. 525.02 kilonewton per meter squared. That's the answer to the differential pressure, which is delta P from this formula here. So that's solution to question number 3. That's solution to question number 3. The question number 4 is a theoretical question that deals with devices, safety devices in the industry, and where we are dealing with a ruptured disc as an industrial safety device. So the question says, describe the principle of operation or an application of ruptured disc as an industrial safety device. Okay. So the ruptured disc is one important safety device that is used to protect people and the industrial system and environment from pressure, over pressure, and sometimes under pressure. So, but most especially over pressurization. So a ruptured disc is a safety device which with a set breaking point that reacts to a certain pressure and is used to release pressure in a number of applications. And then the other names that they call it in the industry is a pressure safety disc, burst disc, bursting disc, or a burst diaphragm. In the process, the device guards against overpressure and vacuums that could harm people, that could harm environment, and also machinery. So can also harm machines, can harm the environment. So the device relieves over pressurization or vacuum pressure under pressurization, so to say. And the purpose of ruptured discs is that they shield process piping system, equipment, and pressure vessels from harmful vacuum situations or overpressurization. And this is a device that is non-resealing. That is, when you use a ruptured disc and it's operated, it bursts the diaphragm in it, and then it's not resealing. You have to replace the diaphragm. Now, the two most often utilized pressure protection devices in industrial plants are the ruptured discs and the pressure relief valves. And for the ruptured disc, it contains a disposable diaphragm that once bursts, you have to replace it. And this is a device that has been designed to burst at a specific differential pressure, whether gauge or vacuum. And so when there is a negative pressure that is positive, when there is either positive pressure or negative pressure in a process piping system, the ruptured disc will react immediately by bursting. So after it has ruptured, it does not receive. So it has to be replaced in order for the system to be put in place again. The ruptured disc has to be replaced. That's the operation of the ruptured disc. That's the use and operation, the principle of operation and application of the ruptured disc as an industrial safety device. So that's how we come to the solution to question number 4 and the end of the solution to all the problems. Do not forget to give us a thumbs up in this video, that is, like the video and share. Also, if you are new on the channel, do not hesitate to subscribe to the channel and then click the notification bell so that when we bring another interesting videos on engineering, instrumentation, computer, or mathematics in this manner, you will be notified by YouTube. So thank you very much for watching. Until another time, when we bring another fine video like this, we say bye-bye.